Greetings. In this video, I'll be using modular arithmetic rules and properties connected to modular arithmetic in order to solve an interesting problem. It is as follows. I have the number 34 to the 321 power. And the question is, if I divide this by 13, so this will be a huge number, by the way. Imagine doing 34 times 34 times 34, 321 times. That will get a very high number. I want to divide it by 13. I want to find the remainder. In other words, I'm doing 34 to the 321 power mod 13, modular arithmetic. There's a shortcut for that. Mod 13, you can imagine it like a clock, which after it reaches 12, it goes back to 1, 2, 3. So, and until it reaches 11, 12, and then again, it loops inside this basically 0 to 11. Modular arithmetic, what it does is basically it gives you the remainder after dividing by whatever the mod value is, or in another way you can imagine it is basically once you get to a certain value, it loops back to the first value, namely with some groups, integer modulo groups. Let's say we have modulo 5, integer modulo 5, we'll have 0, 1, 2, 3, 4, and if I take for example 17 mod 5 on this group, or if I have addition on this group, I do 3 plus 5, because there's or 3 plus 7, because there's modulo 5 is I get 10, but I have to divide it by 5 and take the remainder. So in that modulo arithmetic, it will have value 0 in the end. But not to slide in that direction. For now, we will care about this. And namely, this is possible to do using software, not using usual calculators probably, because that will be such a big number. Might happen that smaller, simpler calculators not able to do this. Computer software, advanced computer software is prepared, and it actually indeed very probably uses a similar idea that we'll be doing here. There's explicit algorithms formulated in various ways, but in this one, I'll purely be using the properties of modular arithmetic in order to tackle this problem, in order to get the remainder of dividing this huge number by 13, and what the remainder is, without having to actually write out the number. And we'll be using modular arithmetic rules for that. So namely, the idea will be as follows. I will be rewriting the exponent in a way so that I can rewrite this entire number as a multiplication of more things. Because if I can rewrite the exponent as an addition, then addition in the exponent gives us smaller terms that multiply each other as a rewriting possibility. That means 321. Well, the idea of binary numbers, by the way, is they record the particular powers of 2 that you add up together in order to give this number in decimal form. So, if I want to convert into binary, as we had done in a previous video on this channel, we'll now be using a similar idea. So basically, what I'm saying here is, still our goal is the same. What is the remainder after dividing by 13 this 34 to the 321 power? But first of all, the first step will be I'll be rewriting the exponent we have on here. And I'll be rewriting it in a way such that I write it as only an addition of different powers of 2. And I'm doing that in such a way that I always first choose the highest possible power of 2 that fits inside the number. So what is the highest possible value of 2 that I'm doing as the first step in basically breaking this number up as an addition of different powers of 2? And it is possible to write any positive integer as a combination of single multiples of different powers of 2. Now, what is the biggest power of 2 that can fit here? That's 256, which is 2 to the 8. 2 to the 8, alright? So after I have 256, I still have 65 left. And so again, I look for another power of 2 that fits inside that 65. And I'm looking namely for the biggest power of 2 that fits into 65, which is 64, which, judging from this is 256, it will be 2 to the 6th. And then after that, I only have one unit left until this value together reaches 321. Now this is 320. We only need one left, and there's just one option to do with powers of 2, namely 2 to the 0. That means that I can rewrite this thing as 33 to this exponent mod 13. So we are no longer, we are taking still the mod of the same number, we just wrote it in a different way. And by this, I can rewrite it further by properties of exponents. as this times this times this. Alright? And all of this mod 13 still. That's the idea here. And now that I have it rewritten like this, I can start applying these modular arithmetic properties. And one of the basic ones to take into account, and actually it's the main one and the only one we are really using. We'll be using this property throughout the rest of this solution, and it is as follows. Let's take 63. If I have 63 and I want to get mod 7 so mod 7 might divide 63 directly, that would be 0. In any case, let's say mod 5, well, the remainder should be 3, so the solution should be 3. But another way to approach it is, I can break out 63 into the product of two numbers, of two integers. And then I take modulo of each of those first, then I actually put into product these modulo solutions, and then that as a whole I put into modulo. So I can do 21, because that's one factor of it, mod 5, times, what's the second, that's 3, mod 5, and all of that mod 5. And it should give me the same remainder as the remainder of 63 as a whole. So this is 1, this is 1, this is 3, and all mod 5, well, 3 is below 5 in any case, so that is straight away result 3. And that's exactly what we expected. Now, there's proofs we can do for this in general, but I'm just saying that this property applies, and it applies here as well. So, when I have this written, how I can also rewrite it, and that's the main property of modular arithmetic that we're using here, is that I can also inside out apply it. So of course, modulo 13 is on the outside, but I can also apply it individually to each of these components of this product. Meaning, I say this mod 13 and that times the second thing, mod 13, times the third thing, which is 34. And all of that, mod 13. So under this modular arithmetic, this and this are equivalent expressions. And thanks to this fact, I've gotten into a very more simple case, or simple situation. So I can delete these previous steps, although they were important. If you want to replay it, you can go back in the video. And I'll move this information a bit to the top, so we have more space. Well, this will stay for now. I'll keep this same, and 34, actually I might keep everything same. Just running it a little higher. Now, we can already see by head. 34, mod 13, is the only first degree 34 we have here. Well, 34 mod 13 should be 8. So the result of this is already 8. But I'll write it systematically, I'll keep it there like it is. And you'll remember that it's 8. And all of that we take mod 13, although it will turn out at the end that in this case we won't need to this outer mod 13 because already the inside will be below 13. And once already inside is below the mod value, then the mod value won't change it. Alright, and we will remember this is 8 already. So this is our first big step. And the second big step is to realize we can apply similar property or basically the same thing on these high powers. One could say, okay, so we had 34 to the 3 to 1, and we decreased it. Now we have first degree, but we have to still tackle these two. We have to get the mods. Okay, so we know 34 mod 13 is 8. So we've got that. Now, if these other two numbers ended up as small, then we could multiply them and then take them mod 13. Still, that could be a small number, enough for us to do in the head, because we want to do it without calculation, using some computer or software. But the question could be, we had a big power here, and now we got what? We got 60 to the 64. Still, that's a very high one. And this one is, no, this is 64, and this is still 256. That means that it's not really lower. But the advantage is we targeted it at the powers of 2. And that allows us to very, very much play with it and decrease the powers slowly and apply the modular arithmetic on the way. And I'll show how that plays out. So basically for now what I can do is I can, let's say we'll now work this one. and we will figure out what this is equal to. So 34 to the 2 to the 6 mod 13. We have to be careful about the exponents here. It's not that 34 to the second and all of that to the 6. That would be easier for us, but it is rather 34 and the 2 is to the 6. So it's more like this. And therefore, it is just rewritable now as 34 to the 64 mod 13. And that is still a big number. We have this 64 right there. So it's almost comparatively high like this one. Now, the idea is we have this as a power of 2. And that allows us to play with it a lot. We can actually play with it in the way that we can say this is 34 to the 32 times another 34 to the another 32. That is a whole mod 13. And we know that when this modulo 13 is applied from the outside, we can also first of all apply to each of these. And we can break it down even more. We can do a lot less than that. We can do it the way that we will use powers. And thereby we will basically, and we know that this, for the multiplication, this modular arithmetic property applies. We can apply to both of those factors. And if we do powers, well, that basically is the base. Below those exponents are those factors. And we can apply the modular arithmetic on those very low ones. So what I can do is I can say, well, not only is it this, but I can say it is namely the same like, let's say for example, just 34 mod that on itself, mod 13, and that to the 64 mod 13. First of all, I can do that, and I already know that 34 mod 13 is 8 from this one because here it was first degree already. So now we have 8 to the 64 mod 13. But what I can now do is I can put there one more power and put the mod 13 on the inside once again. So I can, let's say, take away a 2 and use exponent properties. So I can do 8 to the second and then to the 32 mod 13. That's still the same expression. But what I can do now is in between I can put mod 13 here as well, because that will be the multiplication. This will mean that I multiply 32 times, and we know that for multiplication we can put the mod individually to each of them. So I can show that with the powers. So 64, this is 64, and I can do 64 mod 13 on the inside as well. And then the 32 will be on the outside of this mod already operation. So we basically put the mod 13 once again inside. Now 64 mod 13, that ends up being 12. So we have 12 to the 32 mod 13. And again, we take one less power. We divide this using exponent properties. So what we do is I can do 12 to the second and all of that to the 16. I basically break up this exponent. All of that mod 13. But again, I can put the mod 13 on the inside as well, because those are factors of a chain of multiplications. That's what the exponent means. And I can do 144 mod 13, that to the 16th power, and from the outside mod 13 once again, on the whole thing. Now, here it ends, and we don't have to continue doing this chain, because fortunately enough, the mod of 144, if the mod is 13, that's 1. It's 143, and the remainder is 1 for multiplying it to the second power basically. So the 13. So yeah, 144 mod 13 is equal to 1, and that is raised to 16. So now we don't have to continue anymore. It will forever stay 1, and mod 13 of 1 is 1, because this is simply 1. That won't change. So something lower than the mod that higher number than the number that was put inside is still the same, doesn't change. So this is equal to 1. So all these operations, all this work told us, or let us know, that this thing is equal to 1. For this reason, it has already started simplifying very much. So this is equal to 1 we now know. And I would say that this is very, very similar. This is very similar case. And we might actually already almost skip this one. Or we can almost skip this parentheses, just saying that if this was 1, then it should be 1 as well. there's a way to prove directly, and you can prove for yourself, or I can show it right now. So 34 to the 2 to the 8, that's to the 256, right? And we do mod 13. But we know that 34, but we had, first of all, we can apply it again inside. Oh, I can do it from the first step again, theoretically. This was 64. So what I can do is I can say 34 to the 4, all of that to the 64, mod 13. Alright? And then what I can theoretically do is, well, I can again take the same steps. I can put it inside out, and without doing those small steps, I can actually I can do it inside out. First of all, mod 13 on this is 8, alright? And then I have it to the second power, and then again to the second power, and then to the 64 power, mod 13. But we know that mod 13, mod 13, mod 13 would go inside each of these stages. So the mod 13 for 64 was 12. Alright, so mod 13 for this, I can actually the 64 would be basically, yeah, so that would be 12, and that is squared, so 144 mod 13. Mod 13. But remember that 144 mod 13 is 1. And so we are left with this. 1 to the second to the 64th mod 13, which is again 1. And so even this is 1. And through this is kind of a proof that both of these parts, which looked far more complicated, actually end up just giving the remainder of 1. So this is 1 as well. And for this reason, we can just follow the very basic scheme that we had created in the beginning, and it was as follows. We broke it up into a multiplication, and we know we can apply to each of these multiplications the mod individually. So 1 mod 13 is 1, then times 1, and times, we know this is 8. And then as a whole, we apply mod 13. And as I said, this mod 13 is not needed anymore because this 8 is lower than the 13 itself. So the result is 8. So by this calculation, we got to the result that the number 34 to the 321 power, when divided by 13, the remainder is 8. And one could use concrete algorithms formulated in various ways, which are quicker if you do this many times and so on. But in this way, how we do it now, how we viewed it, how we approach it here, is the only thought you had to keep in mind was the modular arithmetic property of under the multiplication that you can repeat it inside, and is basically transferable to the idea of exponents as well.